Steel is the world's most important engineering and construction material. It is an alloy of iron and carbon, in which the carbon content is less than 2%. It is the most widely used material that is needed in every aspect of our lives, for building and to fabricate things such as cars, refrigerator, washing machine, ships, and surgical instruments. The main reasons for its popularity are the relative low cost of production, availability of its raw material, and its diverse range of mechanical properties. There are more than 3,500 different grades of steel, with many different physical, chemical, and environmental properties. In general, steel is broadly classified into 4 types. They are carbon steel, alloy steel, stainless steel, and tool steel. This video will discuss the weldability of these groups of steel. Welcome to James Sword Research Channel. Endeavor to watch till the end for better understanding. If you find the video useful, like and share the video, subscribe to the channel, and turn on notification for more content. What is weldability of steel? Weldability of steel, also known as joinability of steel, refers to the ability of the steel to be welded. The steel's weldability is used to determine the welding process and to compare the final weld quality to other parts of the steel. For steel, 3 major failure modes by which the weldability can be measured are 1. Hydrogen-induced cold cracking, 2. Lamellar tearing, 3. Spot welding peeling. The weldability of steel, with regards to hydrogen-induced cold cracking, is inversely proportional to the hardenability of the steel, which measures the ease of forming martensite during heat treatment. Factors affecting the weldability of steel include 1. Chemical composition, 2. Physical properties, 3. Heat treatment. Weldability of carbon steel. Carbon steel is a steel with carbon content from 0.05% up to 2% by weight. According to the American Iron and Steel Institute, a steel is considered to be carbon steel when 1. No minimum content is specified or required for aluminum, chromium, cobalt, molybdenum, nickel, niobium, titanium, tungsten, vanadium, zirconium, or any other elements added to obtain a desired alloying effect. 2. When the specified minimum for copper does not exceed 0.4%, or when the maximum content specified for any of the following elements does not exceed the percentage noted: manganese 1.65%, silicon 0.60%, copper 0.60%. Carbon steel is broken down into 3 classes based on their carbon content. Low carbon steel, 0.05% to 0.25% carbon content. Medium carbon steel, approximately 0.3% to 0.6% carbon content. High carbon steel, approximately 0.6% to 1.0% carbon content. The ease of welding carbon steel largely depends on the amount of carbon present. An increase in the carbon content affects the strength, hardness, and toughness of the weld. As the carbon content increases, the weldability tends to decrease. This is because the increase in hardness makes the steel more prone to cracking. The effect of carbon is much less in arc welding than in gas welding. 0.27% of carbon have good weldability with any welding technique. 0.35% of carbon satisfactory welds can be obtained. A structural steel containing more than 0.36% carbon and susceptible to the formation of hardening cracks require preheating before welding and subsequent heat treatment. Application of filler metal with a low carbon content enables hardening of the weld to be avoided. Weld strength can be ensured by alloying the metal of the weld with manganese, silicon, and other elements. Carbon steel having phosphorus greater than 0.04% has an unfavorable effects on the mechanical properties of the weld, since the brittleness is increased. Sulfur has an extremely detrimental effects on the weldability of carbon steel, since it causes red shortness. Cracks is observed at a sulfur content over 0.04%. However, most carbon steels are still weldable. Weldability of alloy steel. Alloy steel is a steel that is alloyed heavily with other element to improve its mechanical properties. The alloyants include manganese, nickel, molybdenum, tungsten, vanadium, zirconium, etc. Alloy steel is the most difficult material to be welded because of its microstructure and its improved mechanical properties, which are good strength, superior hardness, higher corrosion and wear resistance, etc. Difficulties encountered in the welding of alloy steel include: 1. Burning out of the alloying elements. 2. Precipitation of carbide during heating. 3. Air hardening of the deposited metal and the transition zone. 4. Development of shrinkage stresses. 5. Formation of cracks due to low heat conductivity of certain grades of alloy steel. Alloy steels are generally welded, but it is important to know the service joint configuration and subgroup of the material type. Correcting the difficulties include: not allowing overheating, strictly observing the prescribed welding conditions, using fluxes and coatings of special conditions, preheating the work before welding, heat treatment after welding. Weldability of stainless steel. Stainless steel is a type of steel which have good corrosion resistant due to the addition of chromium and other alloying element. It is a group of corrosion-resistant ferrous alloys, containing more than 10.5% chromium and less than 1.2% carbon. The chromium content is key. It reacts with oxygen to create a passive layer that prevents oxidation and protect the steel from rusting. Based on microstructure, broadly 4 major categories of stainless steel are available. They are austenitic stainless steel, ferritic stainless steel, martensitic stainless steel, and duplex stainless steel. Structure of welds in stainless steel can be predicted on the basis of the chemical composition because of the different microstructure the alloy group have. In austenitic stainless steel, the type 304 grade is the commonly used alloy for welded fabrication. They can be readily welded using any of the arc welding process. They exhibit good toughness because they are non-hardenable on cooling. There is no need for pre- or post-weld heat treatment. Weld cracking and heat-affected zone cracking can occur in austenite stainless steel. Weld metal solidification cracking, more likely to occur in fully austenitic structure, which are more crack sensitive than those containing a small amount of ferrite. Austenitic stainless steel alloys are normally welded with fillers, with matching composition to the base metal. Though, there are few exceptions. For example, 308 fillers is used for alloy 302 and 304 type. Type 347 filler is used for 321 type. Ferritic stainless steel is a form of stainless steel generally with no nickel. Commonly used alloys include the 430 grades and the 407 grades. The main problem when welding ferritic stainless steel is poor heat-affected zone toughness. A coarse grain heat-affected zone will have poor toughness. Excessive grain coarsening can lead to cracking in highly restrained joint and thick section material. If ferritic alloys are being welded in section less than 6 mm thick, any loss of toughness is negligible in a piece that thin. Therefore, no specific precautions are necessary. In thicker material, a low heat input to minimize the width of the grain coarsened zone and an austenitic filler metal to produce a tougher weld metal is necessary to use. Preheating ferritic stainless steel will not reduce the grain size, but it will reduce the heat-affected zone cooling rate, maintain the weld metal above the ductile brittle transition temperature, and may reduce residual stresses. Preheat should be limited to 50 degrees Celsius to 230 degrees Celsius, depending on the composition. Martensitech stainless steel are strong and durable. The principal difference, compared with welding austenitic and ferritic grade of stainless steel, is the potentially hard heat-affected zone martensitech structure. This type of steel becomes hard and brittle upon cooling, making it a great material for wear resistance, but more difficult to weld. The high hardness in the heat-affected zone makes this type very prone to hydrogen cracking. Risk of cracking generally increases with the carbon contents. However, martensitech stainless steel can be welded with careful precautions. The filler metals should generally match the chromium and carbon content of base martensitech metal. Other precautions, which must be taken to minimize the risk, include using low hydrogen process and ensure the flux or flux-coated consumables are dried. Preheating to around 200 to 300 degrees Celsius. Carrying out post-weld heat treatment. Duplex stainless steel possesses both austenitic and ferritic characteristics. In terms of weldability, duplex stainless steel are capable but not exactly exceptional. When welding duplex stainless steel, one must be very careful with temperatures. Using either too little or too much heat affect the structural integrity of the steel, rendering it useless. Preheat is not normally required, and choice of filler is important, as it is designed to produce a weld metal structure with a ferrite-austenite balance to match the parent metal. Weldability of tool steel. Tool steel is famous for being hard. It is used to make tools like hammer. It is made from iron and carbon with added elements such as nickel, molybdenum, cobalt, or tungsten to give extra hardness and resistance to wear. Tool steel is also toughened up by a process called tempering, in which steel is first heated to a high temperature, cooled very quickly, then heated again to a lower temperature. The main problem in welding tool steel stems from its high hardenability. Weld cool quickly once the heat source is removed, the weld metal and parts of the heat-affected zones will harden. Stresses from this hardening transformation are normally high, and risk of cracking is possible. Therefore, it is necessary that all possible precautions be taken to prevent or at least reduce the stresses that cause this cracking.